Welcome everyone to session 3 of the online mentorship program. Thank you for joining us today. Today we're going to go through the geophysical surveys and borehole siting in a bit more detail. Last week we went through the overall groundwater resource development process. This week we're going to focus on specifically the geophysical survey and borehole siting aspect of it. We'll go through the mentoring objectives, the schedule I've left out today. The 4 main aspects we're going to focus on is planning a geophysical survey, the electromagnetics, the EM34 method, the Proton Precession Magnetometer magnetics method, and then electrical resistivity tomography, or ERT, or just resistivity. These are the 3 main methods that we use in groundwater exploration. The other ones are either a bit too technical to do, like your seismics, or we don't do it unless we absolutely have to. And then we'll go through our questions again. Okay, so the objective of the online program is to provide base level, entry level data for young scientists, and just give a basic training and give you guys an opportunity to learn the basics without having an internship, because the opportunities are limited at the moment. The first section of the presentation we're going to go through today is planning a geophysical survey for groundwater exploration. And the objective of a geophysical survey is to identify potentially water-bearing features within the underlying geology at a site. And again, I mentioned it last week, but the key word here is potentially groundwater bearing. There is no method out there that exists at the moment that can show you there is water there or how much water there is. They're working on it, but it doesn't exist as far as I'm aware. A good desktop review and a hydrocensus investigation for the site region play a crucial component in the planning of a successful geophysical survey. As from these components, you can get a good overview of the geological formations at a site, the hydrogeological characteristics such as your aquifer types, the depth of the aquifers, etc., and then your site topography and the infrastructure at the site. Your geological and hydrogeological information plays a critical role in your method selection, and then the topography and infrastructure plays a role in the actual planning of the geophysical survey. And some of the most important techniques used in groundwater exploration and the required contrast that they show include the gravitational method, which is it picks up a contrast in earth material density, the magnetic method, which requires a contrast in magnetic field properties of earth materials, electromagnetic methods, which requires a contrast in electrical conductivities of materials, then the electrical methods, such as resistivity, which require a contrast in the electrical properties of the earth materials. Now with this, the key thing with geophysics is that it shows you a contrast. That is all that geophysics shows you. It will show you that one thing is more than the other. It's more dense, it's more conductive, it's more resistive. So without understanding the geology of your area or the expected characteristics of your area, the geophysics doesn't really show you a precise answer unless you know what to look for. And the key references that I've used in this, putting this presentation together, is these Kirsch and Molson. These ones you can have a look for, but these are sort of the 2 main ones that I've used. Okay, so some of the key questions you have to ask yourself when you're choosing your geophysical method is, how big is the site? So how much space do I have to work with? Is it a 10-hectare site? Is it a 1 acre? Is it a small household? What is the size of my site? What is the dominant geology or the main geology of the site? Is it igneous? Is it sedimentary? You know, what are the main units there? What aquifer types are there? How deep are the aquifers? So that'll determine how deep you need to look with your geophysical survey. Is there existing site infrastructure? Is there houses, pylons, fences, underground infrastructure such as pipelines? Yeah, anything that could affect your geophysics negatively? And are there any cost or time sensitivities on the project? Yeah, does the client want you to do the whole project for less than whatever amount, 5,000 Rand, or does he want it done in a week? Yeah, because some of these methods take time, and if you don't have that time or you don't have that budget, you may as well write it off from the beginning. And this is the geophysical methods that we commonly use, the magnetics, EM, and resistivity. So with the size of the site, your minimum traverse length that you require, for magnetics, there's no real limit. You can do a 10-meter traverse. It won't show you anything, but if you're right on the edge of a contact, it might show you something. EM34, you need 50 meters, usually at least, to get something useful. And electrical resistivity, you need at least 200 meters. Maximum penetration depth, magnetics measures the Earth's magnetic field, so there's no depth limitation there. With the EM34, you typically go 25 to 30 meters. It can go up to 60 meters in some circumstances, according to literature. And then resistivity, you can go 120 to 200 meters, depending on how long your traverse is, and then also your electrode spacings. The magnetic and EM methods are both quite sensitive to your infrastructure, your power lines, etc. But the resistivity is generally a bit more, well, how could you say it? Yeah, robust. It's not as sensitive to site conditions. Most economic is your magnetics, because you can do it with just one person. EM is not that expensive, but you do need 2 people. And resistivity is the most expensive because it's quite specialized equipment. And you need a team of people to lay out the cables and to do the actual survey. Physical constraint considerations you need to take into account when you're planning your survey. First one, and the most important one, is can the drill rig actually get there? Don't plan your survey in areas that are restricted for the drilling machine and the equipment that you need to actually drill the borehole. Yeah, and also make sure that you can get there. Yeah, rule of thumb is if the bucky can't get there, the rig can't get there. Because this is sort of one of the bigger rigs. But, you know, I always like to take my vehicle, which is just a 2-wheel drive SUV. And if that can get into the site, then usually the drill rig, which is a 6x4, can get in. Then you've got to look at areas like under trees and stuff where the rig can't get its mast up, because the mast is quite high. You know, that mast there is probably about 12 meters, 10, 12 meters. So you need to make sure that you don't have any overhanging trees, because they're just going to get knocked over. Other considerations is areas with existing or proposed routes for surface and subsurface services, your cables, pipelines, etc. Areas with foundations or underground structures, and then areas where you wouldn't be able to install your pump equipment. So again, if you need to get a crane in to install your pump equipment or something like that, you know, you need to avoid that for your geophysical survey. Environmental constraints that you have to take into consideration are those areas where the existing environment could either impact on your borehole or be impacted on by your borehole. So that's areas where there's contaminated surface water or stormwater runoff going past the borehole and potentially entering the borehole. Areas where there's support for agriculture, where your storage for fertilizers, cattle dips, etc. This picture here, the borehole got run over by a bulldozer. Even though it's in the middle of nowhere, they still ran over the bulldozer. The area where you got your disposal of waste fluids and materials, such as your pit latrines, landfills, septic tanks, mine tailings dams, etc. Areas within a buffer zone of your surface water bodies. And then areas where you've got with areas supporting the development of formal or informal settlement or industrial activity and underground fuel storage tanks, just because those are potential sources of contamination for your borehole. So this picture here, you can see the collar of the borehole. When we installed this, this was a 0.5 meter high. And because they were dumping all the silt and stuff, it was like a runoff area for a cement packaging plant. It's almost covered the borehole entirely. And this one here is like a copper byproduct dump, and the copper inside this borehole went from about 0.1 milligrams per liter up to about 5 in 6 months. So you've got to plan to be away from these things. Okay, is everybody following so far?
Yes, sir.
Yes, we are.
Any questions on planning your survey so long?
Very interesting. Thank you, Matthew.
Thanks, Terence. Appreciate the feedback. Okay, so can I carry on to the electromagnetics section of the presentation?
Yep.
Yes. Great stuff.
Yes, you can.
Cool, so on we go. Okay, electromagnetics, the EM34-3 method is one of the more common ones we use in groundwater exploration. But it does require 2 people, so that's why it's not the most expensive, but it's not the most economic either. The electromagnetic method uses the principle of induction to measure the electrical conductivity of the subsurface. And you've got 2 broad categories for the EM fields measured, namely your time domain, or TDEM, or your frequency domain, your FDEM. We use the FDEM typically in groundwater, where a varying magnetic field induces a current into the ground so that the amplitude is linearly proportional to the terrain conductivity, with the magnitude of these currents measured by the magnetic field that they generate. Oh, it's a lot. And you see here we've got what the EM34 looks like. You've got your receiver coil over here with a receiver box. Can everybody see my mouse on their screen?
Yes.
Okay, great.
Yes.
Okay. So on the left, you've got the receiver box and the receiver coil, then the transmitter box and the transmitter coil. You can see the transmitter coil is a little bit thicker than the receiver coil, and it is quite substantially heavier, when you're lugging it around the field. And then here is the coil just joining the 2 together. Okay, so you use it at specific or specified coil spacing with 2 operators doing the survey. This is what your transmitter box looks like. You've got this that plugs into your coil, and then the coil plugs into the cable, which then goes through into the box, the receiver box. So your cable, but your coil between, or your cable between the coils plugs directly into the receiver box, and then the receiver box also plugs into the receiver coil. So the EM34 measures the in-situ electrical conductivity of the subsurface by using a controlled source to send electromagnetic waves into the ground, which then results in induced currents in the earth materials. These in turn cause electromagnetic waves, which are interpreted in terms of the primary and secondary magnetic fields to determine the apparent conductivity in millisiemens per meter for the subsurface at a specified point. Is everybody sort of with me up till now?
Yes, we are. But I have a question.
Yes.
So now, how would you know like the difference? Because with the electromagnetic conductivity of the water be higher than that of like the normal ground, like soil surface above the water, or like how would you know the difference when you've like contacted water underground using this method?
Yeah, you see that the thing is, you don't actually pick up water.
Okay.
You know, that's what I was saying right in the beginning. You know, you're picking up your potentially groundwater bearing fractures or contact zones. So you'll see an increase in conductivity. We'll go through the different anomalies and the shapes and all those kind of things during this presentation. But you don't pick up water unless you got like a clay or something. Your clays, you'll see it. But, you know, otherwise you won't see water as such. You'll just see a more conductive fracture zone or contact zone or something like that.
Oh, okay. Thanks.
Okay, then you have to interpret that and say it's likely to have water there, or it's, you know, this is a dead patch. Okay.
Thanks. Thank you.
No problem. Okay, so the coil separation for the EM34 is either 10, 20, or 40 meters, which determines your depth of survey penetration. So in general, sort of rule of thumb is 0.5 times your coil spacing is equal to your depth. So if you got a 40-meter coil spacing, you're looking at a penetration of 20 meters. It can go up to about 30 meters. Sometimes they say it's even 40 meters, depending on what earth material you're working with. And then this is how the survey looks. You've got your either transmitter or receiver at the front, and then your other coil at the back. And you can see how they're aligned. You need to align them because if one is facing another direction, you know, it causes secondary currents and then you get bad data points. So they have to align with one another when they're in the vertical position and also when they're in the horizontal position. They need to be in a sort of common plane. Otherwise you get nonsense readings. And then here again, we've got your sort of receiver in the front and your transmitter at the back. Okay, at each measurement point, you change the orientation of your coil. So you're going to go vertical dipole and horizontal dipole. It's sort of confusing in the beginning because your vertical dipole is when you lay the coils flat. And then your horizontal dipole is when you have the coils vertical. The horizontal dipole measures typically the horizontal bodies, such as a contact between a weathered and competent rock. And then your vertical dipole measures your vertically orientated bodies, such as your faults, fractures, or intrusions. When you conduct your EM survey, it's important to align your transmitter and receiver coils. Yeah, as I mentioned before, they need to talk to each other. And then if the coils are not aligned properly, your measurements may be distorted due to the variations in the magnetic fields. Does this make sense to everybody?
Yep.
Okay, we've got one yep.
Yes.
It is making
Yes.
sense.
Yeah, listen guys, it's one of those things where you do it and you kind of just accept that that's the way it is, and then you go back and you look at the theory and you're confused again. Yeah, so it is a tough thing to wrap your head around. Yeah, but we'll carry on. So the field procedure before the survey, you need to remove your cell phones, knives, and all metal things, anything that can give off or accept the electromagnetic current. You take it off of you and you put it in your vehicle, especially cell phones, because when your cell phone rings, it gives off like an electromagnetic pulse, and then your data just goes insane. So that's step one. Step two, check your battery levels of the transmitter coil, receiver, and your GPS. Do this when you're at your vehicle. Yeah, just check all of it. There are buttons on the equipment that let you do that. And you check your coil length, make sure you got the right, or cable length rather. And then you check your cable for any kinks or breaks. You start your traverse at least 50 meters away from your vehicle, away from any fences, over power lines. And then you make sure that your traverse is clear for the survey. Yeah, this is important because you want your traverse to be as straight as possible to get the perpendicular contact between any features that you might have identified. Because we look for a contrast in geophysics, you always want to plan your lines perpendicular to a fault or to a contact zone, whatever you've identified in your geology. And with the EM, it's important to get a clear line because you've got that cable in between you. If the cable is getting caught up on bushes or trees, or the cable can't get wet, it's electrical, it's pulsing, it's sending current into the ground. If this gets wet, it's going to short, and then you're just going to have to stop. So just have a quick look, make sure there's no big things in your way, and then you can start your survey. And then you check the position of your transmitter or your receiver. That's whether it's in the front or at the back. And you want to be getting positive readings on your receiver box. If you're getting a negative reading with the receiver at the back and transmitter at the front, switch your positions, go receiver at the front, transmitter at the back. And then you carry on from there. Then when you do your field measurements, you take an initial GPS reading at both the transmitter and the receiver coils. Remember, these are 40 meters apart, so you're going to be doing it, usually it's going to be at the one in front. That's preferable because then you go, your point one is there at the back, and at the front you've got 40 meters away. So then you're going to go 5-meter intervals, and just remember that you're reading at 20 meters in between those points. And you start with the horizontal dipole, where you got the coil vertical, and you wait for your readings to stabilize. So you'll see your readings, while you get your coils aligned and all those kind of things, your readings will fluctuate. Wait till it stabilizes, then you write it down. And once you've written that one down, you're going to drop your coil down to be horizontal, measure the vertical dipole, and then pick it up, go forward 5 meters, take a GPS reading, and start it all over again. Do the horizontal dipole, then the vertical dipole. So that's what your horizontal dipole looks like. And then your vertical dipole. So does that make sense to everybody, how the field procedure works?
Yep.
Yeah, Bo. Yes.
It's making sense.
Yes, you can proceed.
Okay, great. And I can tell you, EM is probably one of the worst geophysical methods because of the constant up, down, up, down. So you're going to have it up, then you're going to lay it down, then you're going to pick it up again and walk, then you're going to lay it down. So the up, down, you'll get very used to. Okay, so then to interpret your EM data, you need to, yes, Rizani?
I have a question. Your previous slide, you said the other one.
Which other one?
That the picture behind this one.
Mm.
Yes. So you said that it's important to make sure that we identify our vertical structures. I mean horizontal structures like beddings or folding or folds. So is it possible that you might be conducting these electromagnetics in a place where you can't quite, I mean, on the ground level, you can't identify the features?
Yeah, definitely. And that's why it's important in your desktop review to get an idea of how thick your weathered zone is. What kind of structures you're looking for there, because, you know, for example, in the DRC, your weathered zone is about 50 meters thick. So EM can't penetrate that deep. So you're just going to be looking at sand. So EM is not going to work there. Yeah, so yeah, that is important to plan properly and to get your desktop review and your basic understanding before you get out into the field.
Right.
Okay. Does that
Matthew,
help?
Matthew, may I please ask, how many people in general do you need for this kind of survey, for the EM?
Minimum you need 2. Yeah, one to hold each coil. But to be comfortable, you'll have 3. So it's 1 person on each coil and then 1 person writing it down.
Okay, thank you.
Okay. Yeah, more than 3, I mean, there's going to be someone that has nothing to do. Okay, so can I carry on?
Yes.
Great. So in order to interpret your EM data, you need to first understand the principles of the EM34 system, which we've gone through very quickly now. Understand the operation of the particular EM system that you used. You know, we use EM34, but you get the other ones. You get EM31, which is like a pole with a transmitter and a receiver at either end. And it goes up to, I think, EM38. But we focus on the EM34. Then you have to have a knowledge of your geological environment. You know, like I said, if you don't understand what you're looking for, your graphs are just not going to make sense. And then we need to be able to relate your data back to their geological environment. So you need to have a sort of conceptual model almost in your head when you start interpreting your EM data. And this gives you a nice overview of some of the expected. Here's your conductivity for the EM, and then this you can use for your resistivity in an ERT survey. So you can see sort of where your data would lie. You know, give you a good idea of what you might be looking at. Now, to sort of get a high level understanding of the EM34, you consider just the magnetic field. Do you remember in, I think it was in high school or first year physics, where you had your dot and a cross to show which way a current is going along a wire? So this one, the current is coming out of the screen, so towards us. And then the field that it's generating is turning in a clockwise direction. You can see the field vectors here of the magnetic field line. So then here is your ground surface where you're doing your EM. And then you've got your horizontal dipole and your vertical dipole. Does everybody see what I see?
Yes.
Yes, okay. So you can see these two are pretty symmetrical. So this one goes up, then it goes down on your horizontal dipole. And then your vertical dipole goes up here. It crosses 0. So this is your 0 line on the y-axis. Crosses 0 here at your body, your wire or whatever you want to call it, your pipe. Crosses at 0, goes down an equal amount to what it went up, and then it comes up again. So it's a symmetrical type of anomaly. The maximum position on the horizontal, like I said, there is above your conductor. Vertical goes at the crossover position is at the conductor. Okay, so that's a sort of hypothetical situation, which we can then look at a vertical dike, straight vertical dike, which you're not really going to see in nature often. See there again, you've got this little bit of shoulders forming on the horizontal dipole. And then you've got the symmetrical graph on your vertical dipole. Now, when you plot your data, these are going to be on top of each other. So you're going to get the sort of head and shoulders, and then you're going to get the cross point on your vertical dipole. Then on a subvertical dike, this is more like what we see in nature, like in your Karoo with the dolerite dikes, etc. For a subvertical dike, the crossover position is related to the shallowest point of the dike. You see, there is where I've got 0. Over there, and it's not symmetrical anymore on your anomalies there. You see this one dips down a lot lower, comes up, oh sorry, yeah, goes down quite deep there, comes up, and then it goes down there. It's not like this one where it's equal. So the horizontal dipole, the shallow side, or the down dip side, is a lot deeper there. And then the larger the dip, the more asymmetric your anomaly becomes. So if this thing dips shallower and shallower, the more stretched out and warped your anomalies become. And then also with depth, here is ground surface 2, where you've got the deeper anomaly or conductor there, and ground surface 1, where it's a shallow conductor. So here is what your anomaly looks like for the shallow conductor. This is your ideal conductor again. And then with a deep one, you see how it gets wider, but it gets flatter. Everybody see that?
Yes, we can. Well, yes, I can.
There we go. So we'll carry on. So now this is for your vertical intrusives and those kind of things. Now to what we more typically use it for is your weathered zone basement aquifers. So here we've got your solid lines as your vertical coils or your horizontal dipole. So we've got green at a 10 meter spacing, so 5 meters penetration. Red is at 20 meters and blue is at 40 meters. So that is for vertical coils, the horizontal dipole. Then your dotted lines are your horizontal coils or vertical dipole. So your deeper weathering is indicated by your higher readings at about 10. So you see there on both your horizontal dipole and the vertical dipole. You can see there at about 150 meters along my traverse, we've got the peak of the graph. So that's my deepest point. At the shallowest point, it's all fairly similar, regardless of coil spacing, separation. Generally, we want to drill at this deepest point because your water is going to flow along this weathered zone contact, almost like a dam, and fill up into this little trough. So that's where you want to be drilling. It's on this peak of the graph. And this is related to the question we had earlier with how do you know if there's water or something in it. If your readings are above 20, that's most likely clay. So, you know, the clay will retain your water, so your electric current will sort of bounce off of the clay and go straight back up into your receiver. So there's water there, but it's clay water. So you're not going to get it out.
Matthew, I have a question.
Yeah.
So what happens when the HD and the VD cross? When the data cross, when the graph cross, when you plot them together?
Well, that's what's happening here. You see, if you had to draw this up here, your anomaly there is where your conductor is. And then your conductor is there. So if you cross these over, your graphs would cross somewhere around here. Let me do it with a dark.
Is that like one of the drilling points as well?
That's it. It's where you get this crossover of HD and VD. So you'll see right at the end, I've got the sort of target zones that we want to look at. So on a dark, you want to look at the down dip side because groundwater is going to flow along here, pond up. Yeah, it's not going to pond up on this side. It's going to be all the way down here. But at least here, you're going to get this sort of dam wall almost on this side. So where these cross over, which will be around here. Yeah, that's sort of plotting about there on this dark. So you want to get before your main anomaly, typically somewhere around here. So before the anomaly there, and then in this sort of trough zone, just on this area here, sort of halfway up towards the peak, they'll cross over. Make sense?
Yes, it does.
Great.
Hi, Matthew. I also have a question, please. How do you convert the data to depth? How do you convert the data to depth?
You don't really. I mean, you can get an idea of your depth, where it's that your depth is half of the coil spacing. Yeah, but there are equations, but I don't include them here because they're quite confusing, and to be honest, you don't really use them. You know.
Yeah, that's the thing. I don't really get a clear answer with the equations. It's not very clear.
Well, that's the thing, and I mean, in all honesty, in consulting, in academics, you know, in varsity we learned it and we focused on it quite a bit, but you know, in consulting and in sort of practical world, you don't use that. You just sort of say, literature says the weather depth is here. I've used the coil spacing of 40. Therefore, I'm looking at about 20 meters here, and it will make sense or it won't make sense.
Okay, I understand. The horizontal dipole usually gives a very beautiful graph that can relate to a similar graph that MAG gives you on the same traverse. But vertical, it looks like something jumping around. What do you do with that, and how do you interpret that? Especially if the horizontal dipole matches what you see with the MAG, but the vertical dipole is just all over, absolutely all over.
Well, that we'll get to here with the fractured zone. Yeah, I think just hang on to your question there, and then once I've gone through the fractured zones and you see the sort of shapes that we get out here, then we can go back to what you were saying.
All right, thank you so much.
All right, cool. So fracture zones are generally a bit more conductive than the host rock because of your clay content through weathering and because of the water that might be going through them. But the response is quite complex on the EM because of the width of the fracture zones, and also they're not all in the same orientation. You get horizontal, you get vertical, etc. So the horizontal coils of the vertical dipole will show a negative response over a single fracture instead of a positive where it's increasing. This is because of the inducing field, the EM coupling between the inducing field and the fracture. So if you got your fracture here, you see the horizontal, like you were saying, doesn't really do much. but your vertical will show this. This is with a single fracture, but we don't often get just a single fracture in the real world. So your fracture zones are typically identified by your significant noisy readings on the vertical dipole, while your horizontal dipole is quite limited in its response. There we go. So you see, this is what you were saying, is you get this nice horizontal dipole going over here, and then your vertical dipole just does whatever it wants. And you can see there, that's sort of what a fracture zone in the real world looks like. Does that answer your question there?
Yeah, it helps. It helps. Thank you. Thank you, Matthew.
No, cool. So break it down into like, this is what a single fracture looks like. And then you look at the real world where you got this jumble of whatever you want, thick fractures, thin fractures, sub-horizontal, sub-vertical, vertical, and it just does this. But you can see there's your ideal drilling target where it crosses over, going down into the middle of your fracture zone. Over there again, in the middle of your fracture zone. So it sort of answers two questions at once.
Yeah, thank you. Thank you very much.
Cool. Is there any other questions about EM before we go on? I'm going to carry on then to the next method. Yes. Okay, so magnetics is one of the ones that we use most commonly in South Africa, especially with the Karoo, with our dolerite dikes and dolerite sills. Now, magnetics is one of the oldest and the most used, despite only a small number of minerals producing magnetic effects. Yeah, your iron ore is one of the main ones, and then your igneous intrusions, where you've got the settling of your iron and other magnetic minerals out of the lava or magma. Yeah, magnetic field strengths we measure in nanotesla or in NT, with magnetic properties of adjacent rock units potentially differing by orders of magnitude. So you'll see if you're going over a nice shallow dike in the Karoo somewhere where you've got Eka formation, sandstone shales, then you go onto your dolerite dike, you might get an anomaly of 5,000 and above. It'll be a huge jump in your graph. And that's what you want. You want these strong anomalies that are clear as day. And you can interpret them nicely. And it's important to note that your magnetization is a vector quantity, which is related to the north and south poles of a magnet. And there's two situations we need to consider when interpreting our magnetic data. Yeah, and that is your magnetic field of the Earth. The main magnetic field of the Earth originates in the electrical current circulating in the outer liquid core, with a magnetization vector of bodies superimposed on the total magnetic field. And then there are variations in magnetic field intensity and dip at various latitudes across the globe, which you need to consider as when you're conducting your survey, as these can impact your anomalies that you measure on magnetic rock units. And the average intensity in South Africa is between 25,000 and 28,000 nanotesla. And you can see here your equator, and then all of that's your north-south pole. You can see there it goes almost sort of horizontal there, and then it's at an angle at your mid-latitudes. And we're at a mid-latitude. And then this is what it looks like in the textbook. And this is what it looks like in the real world. Yeah, I mean, we probably somewhere around here. Yeah, I don't know what's happening there, to be honest. And this is the map. So your solid lines are your inclination of the magnetic field, which is this angle here. So in South Africa, you see it's about 60 degrees inclination, 60 to, yeah, it's about 60. And then here is on the dotted lines is your intensity in times 1,000 nanotesla. So you got this 30 coming through here. So typically we are down there, so 25,000 to 28,000. Everybody sort of understand that?
Yes, thank you.
Cool. Okay, so magnetic anomalies that you pick up are either caused by induced or remnant magnetism, where induced magnetism is the same direction of the Earth's magnetic field, and remnant magnetism may be in any random direction. So if you think about it, your induced magnetism is the spinning of the core, and your remnant is an intrinsic property of that mineral or that deposit. The degree of magnetization is dependent on the intensity of the field, your F, and then susceptibility of the material. These are some of your susceptibility ranges. You can see your slate or shales is very low compared to dolerite. Greenstone, basalt can be high depending on its mineralogy, but dolerite by far, I mean, it's up to 0.15 and basalt is only up to 0.1. So you can see why we like to use it in the Karoo with our dolerite dikes. And some of the causes of remnant magnetism may be one or more of the following. Cooling of the rock in a magnetic field, and chemical formation or crystallization in a magnetic field, magnetic grain orientation in a magnetic field during sedimentation, and then reorientation of magnetic grains during a metamorphic event. Typically we'll see it as one of the first two in your dolerite intrusions and your bushveld maybe in some areas. The equipment we use in South Africa mainly is a Proton Precession magnetometer, which looks like this. The magnetometer is comprised of your control box, which is this thing on the right here, and then a container of proton-rich fluid with a coil wrapped around it. It's on the inside there. The protons act as small spinning magnets with a randomly orientated spin axes under normal circumstances where they don't impact your coil. Then you apply a current to that coil, which results in an alignment of the proton spin axis with the strong magnetic field generated by the coil. So everything aligns with the magnetic field of the coil. Then you switch that current off, and the spin axes all precess about the direction of the Earth's magnetic field, which induces an oscillating voltage in the coil. And the frequency of this voltage is equal to the precession rate, which is in turn directly proportional to the Earth's magnetic field. So all you need to understand here is that when you push the read button on the Proton Precession magnetometer, it aligns all of the spin axes, and then when you switch it off, they realign and they generate a current, which gives you your reading of intensity on the unit. It's a very simple system. And again, before you begin, you need to remove your cell phones, knives, etc. Leave it all in the vehicle. You check the battery levels on your Precession magnetometer and the GPS. Now, most of the magnetometers that I've worked with, they don't take batteries. You plug them in to charge them. So just make sure you do that the night before you start your survey. Start the traverse at least 50 meters from your field vehicles, your fences, power lines, and then calibrate your Precession magnetometer. Usually we do 25 to 28,000 for South Africa. So up north here in Joburg, we'll do 28,000, but down in like Cape Town and the sort of southern Karoo areas, you might start at 25,000. And most of the newer models will have an automatic calibration. But if you want to do a manual calibration, you'll set it to 30,000 and you'll do 3 readings. And you'll see they vary by quite a lot here. And you go up 2,000 at a time, do your 3 readings and see which one varies the least. And in this case, it is 47,000 for your sort of base reading. you get a variation of about 2 nanotesla per reading. Then you take, in the field, you can either have it on the stick, like this guy has it. You see the stick above your head, or you have it in a backpack. The backpacks can have a stick like this, or they can just have a backpack on your back. The stick is a bit better because even us, we generate a magnetic field to a degree. Our clothing, it's static and all those kind of things. So it's better to have it away from your body. But it doesn't really make a huge difference as long as you keep an eye out for noise. So in the field, you take your initial GPS coordinates and the reading at the first station. And all of your readings should be taken at least twice, where your variance between readings is ideally less than 1, but you can make it less than 5. So you're going to take reading 1, then reading 2, and until you get the difference between readings down to less than 5 or less than 1, don't move on to the next station. Just keep pushing it and see when it stabilizes itself. If it doesn't stabilize, you need to recalibrate the machine. You start your measurement intervals at 5 meters. And when you see there's no variance in your line, the magnetic meter or magnetic readings are a lot easier to look at in the field and do an interpretation on the fly. If you see it's not varying that much, then you can extend up to 10 meters. But if you start seeing a variation, if your readings start climbing by 100, 200 per station, go back and then start doing it at your smaller intervals, 2 meters, 1 meter, just to refine your anomaly reading. Then you plot your data points you collected and generate line graphs with the readings on the y-axis and your distance on the x-axis. And you remove your suspicious data points and your anomalous data points. Those are like your single point anomalies where everything is 28,500 and then you get one that is 35,000. Rather just take that out because that's not an anomaly. That could have just been a solar flare, or you didn't see that there was a tin can or a fence or something there. So rather just take that out. And you can see here, you've got like an ideal, it's got a bit of everything. So you can see there, you get this dip before the peak of your magnetic shale, this stippled line here. Dips down, then it goes up to a peak where it's at its shallowest, and it goes down. And you can pick up a fault line where it's displaced it. You can see you get a more intense reading there. Most intense reading here at the top of this basic intrusion. And then your dike also gives you the dip and then a peak going up. You can see the breakdown of your magnetic body over here. You can see it gives out the magnetic fields in like a sort of semicircle. And at point A, you start getting a dip because it's going against the magnetic field of the Earth. And then here, it's aligning at point D. It aligns with the Earth's magnetic field. You see, it's sort of at the central point of this all body, or whatever it is, this magnetic body. So there you get vector 1 plus vector 2. Here it's vector 1 minus vector 2. So you see negative, positive. Does that make sense?
Yes, it does.
Okay.
Thank you.
We all survived vectors and scalars in high school physics.
Thank God.
Now it's back. So that's where if you go back to this graph, it's a very simple thing. Just think about it. Here's the orientation of my body. This is the field it's giving off. This is the inclination of the Earth's field. And this is the effect that my body has on the Earth's magnetic field. Then you can go interpret it. Look at your geology. Think about it. Break it down into bite-sized chunks and just interpret it one step at a time. Then it'll make sense. And so these are your sort of typical anomalies for a spherical body. You get this big dip at the beginning and at the end, and you get this big sort of steep peak. So, you know, symmetrical, nice symmetrical anomaly. You get a horizontal cylinder, same sort of or similar sort of shape and anomaly. A vertical cylinder, you don't get the troughs in the beginning because your magnetic field is sort of doing this. You know, it's vertical, so it's not, yeah, you've got this kind of big field as well. And then here you've got a thinner magnetic field. So your opposition, like this point A to the Earth's magnetic field, is limited. So that's why you don't get that dip. It just goes up and then down again. Same with a vertical thin dike. The climb is a bit more gradual. Then your thick dike also, it's an anomaly, but it's not like the stark up down. You can see the effect of depth of your bodies as well. It sort of flattens out your anomaly. What is this? Amplitude. Yeah, I think it's amplitude where it's stretched out like that, isn't it, in waves? Or is that amplitude? Anyway, you can see it. It stays at the same sort of reading intensity, but the deeper you go, the wider your anomaly becomes. Okay, so we went through MAG quite quickly. Is everybody happy with that?
Yes.
Yes.
It's one of the simplest ones, I think. Yes, Rizani?
Thanks. I'm not sure if I missed it, but does this magnetic method only, can it give an absolute depth, or even here you get to just I don't know. Do you get the question?
Sort of. Again, I mean, there is, there's equations to do it, but like, to go into them, I mean, I'll post them. I'll do a summary and I'll put it online. I'll just do like a write up, because I do have them. I just didn't include them because in the real world, it doesn't really add that much value to your interpretation. You know what I mean?
Yes,
So look, I'll write
I'm
them
not
up.
sure. But then what do you mean they don't really add much value into my interpretation?
Well, look, if you know your literature review, you've got average water strike depth between 50 and 60. So you're going to plan your drilling to 80 meters up to 100 at maximum. So you know that from your desktop review already. You're never going to rely entirely on geophysics only. Yeah, that's why I say it's not going to add value. You know what I mean? This is not going to be the only thing you're doing. Whereas if you're in a geological exploration, if you're doing exploration for ore deposits or something, then it's going to add a lot of value. But in terms of groundwater, you're going to have other data that you're going to rely on as well. And I'll post it and you'll see the equations are quite confusing.
Yeah, no, I understand.
Okay,
I get
so
it now. Thanks.
I just didn't want to confuse everybody. Is there any other questions on MAG?
No. Matthew, I want to ask, like in terms of charging the clients, right? Do you charge them for like separately for a desktop study and for also the site visits as well, like physically conducting the geophysics, or can you just service them with the desktop studies?
Look, it depends on your business model. Like for me, I'll charge office rates for a desktop review and then field rates for the actual survey. Depending on the sort of confidence required in the study. If they say, no, just go do it, we've designed it for you, go conduct your geophysical survey, then you just charge them for the survey. But if they say to you, listen, we need water, we've got no other options, so we need groundwater, then obviously it's got quite a bit of weight behind it, so you need to be quite accurate. So then you would dedicate time to your desktop review, you would charge for that, and then you would dedicate time to your geophysical survey and the reports writing, which you'll also charge for.
Okay. Thank you.
Okay. So generally, like a good rule to sort of live by when you're developing costs is whatever you need to take liability for, you charge for.
Okay.
Okay.
And then it's not a must that after conducting the report, after compiling a report, it's not a must that you service them for the drilling as well. Because the report, basically, you're just telling them where there's potentially water, right? You don't have to be the one that like drills and offers borehole services.
No, you don't have to. It is nice to do the drilling supervision as well, just to see if you're right. But you don't have to, because often what happens is a client will say, let's site the boreholes, let's see if there's any potential. And then they'll look at it, then they'll have to go get some more funds, or they'll get some investment or whatever, and then they'll come back and drill at a later stage. Because your geophysics survey will cost you, let's say, 40 to 50,000 for a MAG or an EM survey, but your drilling will cost you between 60 and 150,000 per borehole. So they'll do it in like a phased approach.
Oh, okay.
Yeah.
Thank you.
Okay. Any other questions before we carry on?
Yes, I have a question. Sorry for my English isn't my mother tongue. So the interpretation is based to the total magnetic field, or is a kind of reduction or something?
With magnetics, we're measuring your total magnetic intensity on your nanotesla.
Okay.
Yeah.
It's not reduced to a pole or something?
You can do that, but typically we just take the reading of the magnetometer, which is your nanotesla.
Okay. Thank you.
And there are other magnetometer types. There's a flux magnetometer. And that one, I've never worked with it personally, but I think that one might be related to the pole that you're sort of referring to. I think. I didn't include it in here because I've got no experience with it. Okay. So is that all the questions? Anything else with magnetics or EM? No. I'm going to carry on then. Okay, electrical resistivity tomography, or ERT, or resistivity just simply. That's one of the ones that we use more up in sort of Africa, your tropical, subtropical zones where you've got thick weathered zones and you don't have that much information about your underlying geological conditions. Yeah, resistivity is measured by injecting a current and then measuring the resultant potential differences at surface. And two pairs of electrodes are required for electrical resistivity survey. So you've got your current injection, A and B, and then your potential difference electrodes, M and N. Remember these, what would you call it? Remember that the current is at A and B, and the difference, the potential difference is at M and N, because that comes in quite a bit throughout this section. So that's what it looks like here. You've got potential difference measurement here, M and N, and then you've got your injection electrodes A and B. And we don't have homogeneous ground generally in real world or in nature. So the electrical resistivity measures your apparent resistivity, not intrinsic or true. It's an apparent resistivity, which is dependent on the current, the potential difference measured, and the geometric factor, which is calculated from your electrode spacing. So your geometric factor, so current we know because we're charging it. Potential difference we're physically measuring. And then your geometric factor we calculate 1/2 times pi multiplied by 1 divided by the distance between A and M minus the 1/, distance between B and M minus 1/AN minus 1/BN. Okay, so that's this NB, MB, NA, MA. That's your geometric factor. Okay, and there are a number of electrode arrays. Two of the common ones that we use is the Venner and the Schlumberger array, and then also a combination of the two. With the new measurement units, they usually run sort of one run of each because they're quick enough to do it, and they combine the results. On a Venner array configuration, the spacing between all 4 of your electrodes are identical. So AM equals MN equals NB. So you see here, there's your AM, MN, NB, all the same. In Schlumberger array, the potential difference electrodes M and N are closely spaced at a fixed interval, while your current electrodes A and B are moved outwards at an increasing interval. So you see MN stays constant, and then AM and NB gets bigger and bigger as you go on your survey. Everybody understand that? The 2 different arrays.
Yes.
Yes.
Great. Okay, and your depth of investigation is more or less your distance between A and B divided by 5. So you can see with the Venner array, as A and B gets bigger in distance, so does M and N, which influences your geometric factor. And then Schlumberger is easy enough because you can fix your 2 inner electrodes and then you just move the other 2 electrodes to get your penetration depth. Okay, so you use either a 5 or a 10 meter electrode spacing, where your electrode pins, which are these long things here, they're usually about 1/2 meter long, 40 centimeters long, hammered into the ground at the required interval and then connected to your cable. So you use like a crocodile clip. You see this guy is hammering it in and then you clip it onto the cable there. So this is at 5 meters and your cables are typically 100 meters. So that's why you need a minimum of 200 meters to be completed. So you're going to have your one cable lying out that way, connected to your control box. And then you're going to have another cable going the other way, connected to your control box. So you'll have like M and N, then A and B. And then the control box will switch it and pick up the electrodes that it wants to use in the different arrays. Does that make sense?
Yes.
Okay, we got one yes. Okay, so before you begin, you're going to check your measurement unit batteries. Yeah, usually we use a car battery for this. Yeah, because your injection current is about 400 volts, typically. And then, of course, your GPS, you need to check your batteries there. Check the entire length of your planned survey traverses open and accessible. Yeah, this is to make sure, because if you're planning a traverse of 1.42 kilometers, you need to make sure that it's open, because you don't want to stop your survey to cut down trees or to maneuver around something if you don't have to. And then check your cables, check your electrodes, check your clips. You don't want to get to the end of your initial survey line and then you run out of clips, or your electrodes are bent or something like that. Then if you're wetting your electrodes, in dry areas, we'll wet the electrodes to make sure that there's a contact between the electrode and the cable, to make sure that the current reaches the ground. So you got to make sure that you have enough water to do this if you're using the water. Then you lay out the cables. You mark the start point in every 10 meters along the cables with a GPS. So you mark your first electrode, and then every second electrode there if you're using a 5-meter spacing, or every electrode if it's a 10-meter spacing. And your measurement unit or your control box is in the middle of the cables. This is always the case. Yeah, it's right in the middle there. You can see cable 1, 2, 3, and 4. And your control box charges the current electrodes AB, and then it measures the potential difference at your electrodes MN. And it also switches these, so it'll assign it to electrode 1 and 10, or 1 and 5, or whatever it is. And then when you roll over your cables, so if you've got a traverse that's more than 400 meters, you roll over the cable, where you take cable 1 and you put it at the end, and you move your control box over. So this configuration will measure there, then the next one will measure there, and that's how you get your long 800 meters, 1,000 meter traverses. Does this make sense to everyone so far?
Matthew, I have a question.
Mm-hmm.
So where the control box is, like where the control box is that where M and N are measured?
No. Your M and N is on your coils. That's at the electrode. So if you go back to this, you see these are your electrodes here.
Correct.
So those are M and N.
Mm-hmm.
All that the control box does, because the control box will know this is electrode 1, 2, 3, 4, etc. Okay? And it will assign electrode 1 as M, and then electrode 2 is B, and then electrode -1 is N, and then electrode -2 is A.
Oh, I see.
So the control box sort of assigns the lettering and the numbering to the electrodes that you've hammered in along your cables.
I see.
So it's literally, it's a control box.
Thank you.
Yeah, in the very, very old days, you would have to do this manually. You'd only have 4 pegs and sort of various lengths of cable, and you would read like a voltmeter or something in between M and N, and you would charge A and B, and then physically move A and B out.
Hectic.
Yeah, all the old geologists will tell you horror stories about such things. Yeah, but we're lucky. This is just you hammer it in and then it does its thing.
Okay, thank you so much.
Okay. Okay, so you can see this is how it reads. So you got your first reading here.
Matthew,
Yeah.
I have a question. Sorry, I just want to ask, how do we do both Schlumberger and Wiener array in such a setting? Like, do we sort of like play around with electrodes as we move along the traverse?
No, when you lay out your cables, the cables are sort of pre-built. They've got sort of a contact on them where you clip on your electrodes. And then the control box, you'll set your settings on the control box to do either Wiener, Schlumberger combined or dipole, whichever one you want to use. And then the control box will run like an algorithm that says switch between A, B, MN, it'll run its systems. Nowadays we, as the sort of technician, we have very little control, or we don't have that much to do during these surveys. We just got to make sure that we lay it out properly and we make sure there's contact on the electrodes. And then the rest is done by your control box pretty much.
Oh, okay. No, thanks.
Okay. Okay, so here is your M and N, where you read it, and then here's your current going into A and B. So you can see here, it reads from this, where your depth is equal to half the distance between A and B. So it goes in like a triangle. Then you increase your distance here between A and B and M and N, and it goes deeper. So that's why you'll see with your pseudo sections or your resistivity sections, it always comes out like a trapezoid. There's a weird shape here, like a half triangle, half rectangle. And that's also why it's usually better to do more than, it's better to do more than 200 meters. Because if you do just 200 meters, you're just going to get this weird shape. So the longer your line, the better of an idea you're going to get. And this one, I'm just going to play this video for you from the Res 2D invert. This question came up, I think, last week during the session. The software, rather than going through it with you guys, I'll go through it as well if we have time. But this is from the website itself, showing you how to do the interpretation. I'll talk over the video because the music on this video is terrible. So with this software, you get a free version which is limited to, I think it's 8,000 nodes or 8,000 electrodes. And then it only does 3,000 three iterations of the model. So you read your DAT file, which is the file that you get off of your control box. And it'll show you all of your specifications. Then you need to eliminate your bad data points. You go edit. And you can see here, I'm just going to pause it. You can see there's like bad data coming through here because this is your sort of reading platform. And you get these huge anomalies. So you want to get rid of those so that everything is sort of within the same realm. So then you go to inversion damping and damping factors. I'm not going to spend too much time explaining this because this is usually what the geophysicist will do for you. You go your forward modeling method. This is your mesh for the modeling. We use the finite difference method. So you're going to change it from an absolute error to a root mean square error. That just helps it to run a bit smoother. Look, you guys are welcome to go to this website and have a look as well. Your model cells, use the model cells with a width of half of the unit spacing. So if you've got 5 meter intervals, your model cells are going to be 2.5 meters. And there's your inversion again. And you see here's all your data points. You see how it makes this triangle. Because you've only had 2 points where you've had A and B somewhere there to read down to this one. And then B and A over here somewhere to read down to that one. So you see that's why it's better to do a longer line, because this is only a 400 meter line. So you've got a very limited data depth over here. Yeah, here is okay, but over here it's just going to be contoured. So it's not really going to be that meaningful. Okay, then you run your inversion. And this is where the big difference between the demo version and the full version of this Res 2D invert comes in. You see there it's on iteration number 4. On the demo, it only goes up to iteration 3. So you see the difference between your actual, this is what it measured. You see the big gaps in the top here where you've removed your bad data points. And then this whole section here is sort of contoured in your model. You just wait for it to run. Yeah, so then you can choose which iteration you want to see, if it's the final iteration or if it's the first one. You choose your contour intervals. Yeah, that's your coloring. So you can see there at the bottom, your contour intervals. And then if you want to look clever, you can do these. Okay, so I'm just going to skip this video. So that's basically how Res 2D invert works. I'll show you guys just now, just some examples of geophysical data. So once your data has been cleaned and modeled, the resultant section can be interpreted in conjunction with your geological, hydrogeological information for the site and the observations by the survey team. So you form like this triangle of interpretation. You've got your maps, your geology maps, your all those kind of things. And then you've got the actual observations that you make. And then the geophysics, your actual results. Like what do you see? So none of these work on their own, or geophysics doesn't work on its own without observations and your maps, which is what I've been saying sort of the whole way through, is trying to reiterate it for you guys. You see, this is your measured apparent resistivity. This is for a leachate somewhere. Electrode spacing is 5 meters. And you can see here, you got this low resistivity, this big anomaly looking here. And then you've got this lower patch over here with your high resistivity in between it. Now, your first thought, I'm going to pick on someone in the list of participants. Let's see. Let's go Neil. Neil, what's your interpretation of this low anomaly here? Is this, what would you say that is?
Well, you said it's a leachate, so I would say that I've not worked with something like this before, or the leachate, as you say. Well, but I believe that your anomaly that has a low apparent resistivity would be more a solid rock with no how can I say, flow in it. So no contamination if you're picking up contamination with this survey.
Well, just think about it in terms of geology. Forget about the leachate for now. If you saw a low resistivity, remember this is low resistivity, not conductivity. So low resistivity means high conductivity.
Oh yeah, okay, yeah, then yeah, it's the opposite than what I said.
Okay, but would you say that this is like a fault zone or something if you had to look at it?
Fault zone, maybe. It does look like more like a dike on the right-hand side of it, so it may be accumulation of water somehow, or but it can be fault zone, yeah.
Okay. Thanks, Neil. Yeah, so
okay.
This is in your measure. This is before we do the interpretation and the cleaning up and all those kind of things. Yeah, then once we've cleaned it up, we saw that during the survey there was steel construction on the top, on surface. So you see that's actually what it is. And then here's your leachate plume there. Yeah, so look at the difference in the pseudo sections here. Yeah, just because of your surface observation. Yeah, if you ignore the surface completely, your interpretation of your results changes completely. So always bear in mind the environment affects what you're looking at. You don't ignore the environment with your interpretation of the environment. Okay, I'm going to show you just a quick example of ERT survey that we did. I'm going to go very quickly through it. Yeah, this one we did in the DRC. I'm going to go very quickly because I know it's getting late. Let's stop the share there. Okay, can everybody see this map here now?
Yes.
Okay. So the site was located in the outer arc of the Lefillian arc, or the copper belt in DRC. Very complicated geology. Yeah, there's just our explanation of the geology. And here are all of our lines. So we've got the mine series geology here, line 5, 6, etc. So I'm not going to spend time sort of going through this survey. I'm just showing you sort of, we try to go perpendicular to the contact there, perpendicular across it there. This is how we planned it. And then the geophysicist got his sort of expected ranges of conductive resistivity ranges for the different layers. So your RGS, the mine series here. And this is what he developed in terms of desktop data, what to expect. And then this is what we, oops. There we go. So this is line 1. You can see there on the top, we just got laterites. You draw in this contact zone there with the laterites. That's like a high iron content clay. And then you got a contact zone sort of dipping over here of your more conductive, less resistive material there. So this is your weathered zone over here. And maybe a fault zone over here. Yeah, a little bit higher conductivity or resistivity, sorry. Okay, line 2, same thing, laterites all the way along. Maybe a fault zone over here, and then your weathered zone there. And here we actually picked up something quite nice on line 5. Yeah, we could actually see the mine series a little bit. We had the SD unit here, RSC coming through here, RSF underneath it, then borehole targets over here. You see how we've colored it with the different units. Without your geological information, you couldn't do this. So we can see all the different geology units, forms like a basin on site. Yeah, so let me get back to the presentation. Okay, so everybody sort of, let me show you this other one. Can you see this? It's called Mashitu resistivity line 1 and 2.
Yes.
Yes, okay. Now do you see each of these white dots here? That is a reading. Yeah, so that is where you've got A and B, and then it reads down onto this point over here. So that's all of your readings. And this generally, these outer limits here, you don't want to cite anything on it, because you see how dense the data is up on top, and it gets further and further apart as you go deeper down. So this data becomes quite heavily contoured. So generally, if you got something on this lip, you don't want to cite it. You'll put it as like a secondary or a tertiary target. And here again, you can see the contouring. I mean, look at that thing there. Yeah, there's nothing there. That's just one point that sort of distorted all the other points. You understand what I'm saying when I talk about that?
Yes.
Yes. Okay, so we'll stop that one. Then I'll get back to the presentation. Okay, so then so that's resistivity. I've just skimmed it quite quickly, but I feel resistivity is quite self-explanatory in its interpretation. I don't know if you guys agree.
No, I feel that it's more complicated to
Me
interpret.
too.
Is that okay? Why do you think it's more complicated?
Like reading the data from the graph, like you have to know what is happening and be able to properly state what you see, which I feel that is complicating.
It is complicated, but it comes with experience. And also, once you start reading about a site, you look at your geology and you start thinking about it from geological aspects, it starts to make a lot more sense. To just be thrust to show here's a graph with blue, red, and purple, it does look intimidating. But when you've got the background to the site, it's not as scary as it seems.
Oh, I see.
So
Yeah,
look,
also, no, sorry, you can continue. I'll ask my question after.
yeah, I was just going to say the resistivity, it relies on your understanding of the site a lot more than the other methods, but it also gives you a lot more information. The other ones give you a single line with one sort of depth range. Like you think about your EM, if you run a 40-meter EM survey, it's going to be penetrating between 15 and 30 meters at best, average 20 meters. Whereas your resistivity is going to go from 5-meter penetration all the way down to 100, 150, 200 meters even. So you can get a bit more variation, and it'll show you stuff. It'll show you the weathered zone. It'll show you your fault zones. So that's why I say it's a bit easier.
Okay, I understand. But I do also get to the fact that when you say that it gives more more information, because now it's the image is quite clear in a sense where you just have to know what you're looking for in the picture.
That's the thing. You need to defend what you see in the picture. You see a horizontal anomaly. So then you use your geological data to defend that anomaly. Yeah, so
Yes.
sometimes the more data you have, the more complicated it is. But just take a breath, look at all the data, and it'll make sense. Okay, Rizani, what was your question?
Thank you. I do agree that as long as you know the background geology of your site, you might find it easy. But what about if there are historical stuff like pipelines or things that are buried there? Like, how do you then know what you're looking at?
You'll see it because you'll pick up your background, your country rock, your background sandstone shales, whatever it might be. You'll pick it up, and then you'll see this sort of circular, a blob in your section. And then you can say, okay, they did build here, so this circular blob is probably a pipeline. It's unlikely to be related to my geology because sandstone shale is typically a tabular geology. So you can relate stuff back to your geology again. If you've got tabular geology, you're not going to have circular anomalies. Make sense?
Kind of.
It's difficult to explain without that anomaly. We had it once at my previous company where we got a pipeline, and it sort of threw out the whole section because the rest of the section was all the straight lines, contact weathered zone, shale, then sandstone underneath. And then there was this pipeline going through the contact of the weathered zone and the shale. And it was like 2 orders of magnitude lower in resistivity than the rest of it. So you could see it clear as day if you put it in context with what the rest of the site was.
I do understand, but I don't know. I don't really have a lot of field experience, but I would say that to much extent of our geological data, there's a lot of estimations or exaggerations. So you might not fully understand what's underground, what you are looking at. I don't know if you get me. You can't really be 100% sure that, okay, it's shale and sand and whatever.
Yeah, look, I'll tell you something that a geophysicist told me. Yeah, and this is a very experienced geophysicist. I mean, he's been doing it for about 60 years. And he told me, because I asked him a similar question, I said, how can you be sure? And he said to me, the best geophysical tool is a drill rod. You'll never be sure until you actually poke a hole in it. But your job as a scientist is to make sure that you can defend your sort of hypothesis, is that you hypothesize that this is shale sandstone based on X, Y, and Z. You've got enough literature values, you've got enough desktop level data or previous drilling results to say that I think it's this based on these previous observations.
Yes, now I totally agree with that geophysicist.
No, look, we're not always going to be right, and it's a lot cheaper to do a geophysical survey than to drill everywhere. So if we can go from having 0 or 20% confidence in a drill target to 80, 90% confidence, it's a lot better than it used to be. So, and you're never going to be 100% sure. I can tell you now, your heart sits in your throat every time you're drilling on a target that you sighted until you hit the water. That 20, 30 meters of drilling with just dust coming out the borehole you start stressing. You know, you can just start counting the money adding up for the client. And until you hit the water, you're always going to be stressed.
Matthew, I want to ask, would you consider like, would you consider opening up like maybe like a volunteering program or something like that for more field experience? Like, let's say you have projects, would you consider like people volunteering for the project just to gain like field experience?
Yeah, look, I mean, if the opportunities are there, definitely. It's just, you know, at the moment, the industry itself is quiet. You know, it's not just myself. It's not just the small guys. It's your big companies that are also very quiet, and you know, your traveling is a bit restricted, and the investment markets are a bit restricted. So it's the physical projects are quite limited. Yeah, and that's why I want to do the online stuff, because that I can do. But even volunteering, you know, the projects are simply not there. But if it comes along, then definitely.
Okay, that's fine.
Yeah, you know, it's a difficult one, because you want people to get practical experience, and with geophysics, you need practical experience. But not many people are investing in geophysics at the moment. Yeah, not many people are investing actually at all.
Okay. I understand.
Okay,
And
so
I also want to ask, like, in terms of the equipment, right? When I search online, are the equipment like mostly overseas, or like can you buy equipment, or is it like renting out equipment only?
yeah, like most of the time, a lot of the stuff comes from Canada. You know, Canada and the UK. You do get Chinese equipment, but I don't know the Chinese models. You know, for the EM and MAG, it's Geonics, which you get from Canada and the UK. And then the resistivity, the best sort of control boxes, as far as I know, is ABEM, ABEM, which is from Sweden or Switzerland, one of those two. But you typically are like, I rent the equipment, because your starting price for a decent magnetometer is probably in the region of 20 to 30,000 Rand. A second-hand EM34, you're looking at between 75 and over 100,000. And then your resistivity equipment can cost you up to 200, 300,000 Rand. You know, that's very expensive. And to sort of build that equipment, you'll have to be doing projects every week, you know, just to pay that equipment off. So we usually rent. There are 2 or 3 rental companies in South Africa that do everything, and then you got the contractors that do the resistivity, gravity. You do have seismics, but nobody really uses it except for the oil guys.
Oh, okay. I understand. Thank you.
So Matthew, what is the name of the guys who are doing this rental for this equipment?
Well, the guys that I use is EEGS. It is Environmental and Engineering Geological Services or something. I'll have to look it up, and then I'll post it for you guys on LinkedIn. But I've worked with them my entire career. And yeah, then there's the other guys as well that they don't rent the equipment, but they do the work. It's, you know, they'll physically go do the survey for you, and you can maybe just arrange with them that you go with them and sort of assist. But the main one with the rentals is EEGS, as far as I know.
All right, no thanks.
Cool.
Matthew, I want to ask as well. The last week's slides, did you post it on LinkedIn, or did you email it or something?
I didn't. It is on my website. you know, in the download section. So yeah, I just haven't had time to do it on LinkedIn. I'll put up a post tonight or tomorrow morning just with a link to my downloads page. Otherwise, you can just go to the Alicanto Water website and go to the download section. You'll see them there.
Okay, thank you.
Okay. Okay, can I quickly go through just the way you cite the boreholes, and then we can wrap it up and just finish up with any last questions we have.
Sure.
Okay, so you're citing on your intrusions, your dikes and your sills. Yeah, you on a vertical dike, you cite on the down dip side of the dike. Thin dikes, you know, usually a thin dike is highly weathered and it's a target in itself. In the case of a sill, your baked zone around the top and the bottom of a thin sill, on the top of any sill is the target. And then the edges of the sill, the edge of the baked zone, where it goes into the country rock, that's a nice target as well for drilling. Your weathered and fractured zones, yeah, generally they have a higher permeability unless they're clay filled and you have a favored target. This is something that you have to look at in areas where you've got cross orientation of your structures and your faults. If you've got two sets of faults, like one going north-south and one going east-west, you need to figure out which one was there first. Because generally, if you've got an east-west fault system that was cross-cut by a north-south, that's closed now. You know, it's been sort of smeared and closed, so it's clay filled and it's not active anymore. It's not productive anymore. So that's something you've got to be aware of. And when you site on your weathered zones, the deepest section of your weathering should be targeted. Yeah, like here, this is that graph we looked at where your EM sort of reached a peak at the deepest point, and that's where you want to put your borehole. Yeah, so that's your two main targeting sites. And that is geophysics. Does anybody have any more questions to what we've sort of gone through already?
I don't have any questions, but I'd just like to say thank you. This was very enlightening and very insightful.
Thanks for the feedback. I appreciate it.
Matthew, I just have one question about the magnetics. Do you do a correction to a base station, or yeah, because I've done a walking mag where we have a base station and then you do a correction to the base station. Yeah, I don't know if you...
Look, you can do that, and with a walk mag, it's useful to have. Your base stations help with any diurnal variations that you might have.
Yeah.
You know, if you're walking for like 3-4 hours at a time, you might go through a diurnal variation.
Yeah.
But typically, if you're doing your line, yeah, you just do one line at a time. Your diurnal, because they're quite quick, you know, 500 meter line or an 800 meter line will take you about 2 hours at most. You're not going to get that much fluctuation.
Okay.
But with a walk mag, because it's doing continuous reading, it's useful to have a base station.
Okay.